let's now look at some properties of eigenvalues and eigenvectors. That's section 3.1.4. First of all, let's look at the trace. Let A be an n by n matrix. The trace of A is the sum of the diagonal entries of A. All right, so if you use the usual indices, that's what you get. All right, so if you have an n by n matrix and you're looking at its characteristic polynomial, the first term is just going to be either plus or minus x to the n. Then the next term, you'll have a sign, and then what you'll have next to it is just going to be the trace of A. And the last term will be the determinant of A. That's the constant term of the characteristic polynomial. If A has eigenvalues lambda 1 through lambda n, which means that this would factor as lambda 1 minus x, lambda 2 minus x, and so on, then the determinant of A is the product of all of them. And the trace is going to be the sum of these eigenvalues. So if you have n different eigenvalues, this is clear. Otherwise, you'd have to count some multiple times, depending on how many times they divide the polynomial here. All right, so if A is an upper triangular matrix, then the eigenvalues of A are A11, A22, ANN. All right, so if you assume that the characteristic polynomial of A is PA with all of this, then what's the size? Well, the size is the degree of the polynomial. That's how many times x will appear. And so A is a 3 by 3, always squared, matrix. The trace, so we have minus minus 1 to the n, x, so minus 1 to the 3, x3, plus minus 1 to the 2, trace of A, x squared, plus, we don't know, x, plus the determinant of A. And so the trace of A is 4. Let me put that underneath, it looks strange. Right, so this is minus x cubed plus 4x squared plus x minus 8. So 4 is the trace. The determinant would be minus 8. Is A invertible? Yes, since the determinant of A is not 0. And so you get invertibility tied into this. So let's see. This is our old-fashioned invertibility theorem for matrices. If A is an n by n matrix, then following statements are equivalent. For a given matrix, they're all true or all false, and we have the ones from before. And then we're adding 1. So lambda equals 0 is not an eigenvalue of A. So let's see. I mean, we know all of these are equivalent, so let's just look at this one and try to prove that it's equivalent to this one. Determinant is non-zero. So let's say we'll prove that F is equivalent to K, and that's going to be enough. So if the determinant of A is not 0, then that means that PA at 0, which is the determinant of A minus 0I, that's going to be determinant of A. That isn't 0. How do I? Sorry about that. So that isn't 0, and so 0 is not an eigenvalue of A. All right, so now let's start with the determinant of A is 0, then PA of 0 is 0, and that means lambda equals 0 is an eigenvalue. So if F is false, K is false. If F is true, K is true, and so they're equivalent.